folks, Mrs. White here, coming at you with a new lesson. We're going to be looking at section 12.2 today, which is 2 out of 3 sections for chapter 12, so we're almost there. Today we're going to actually learn about 2 tests. It's going to be looking at how do we test for independence and how do we do the homogeneity of proportions. Okay, so how do we test for those 2 things? And what do those 2 things really mean, right? So what we're going to be focusing on today is going to be contingency tables and finding and doing kind of like hypothesis testing with contingency tables. And this is something we did talk about in chapter 4. It's actually section 4.4 if you kind of want to revisit that. Some of the calculations that we're going to have to do are going to be related to stuff we've actually previously learned. So here's an example of a contingency table. It's looking at level of education and employment status. We actually did a bunch of problems with this in section 4.4. So we'd be trying to determine if there's a relationship between employment status and level of education. And one way you can do that is with this type of calculation. This is what we've done in the past. This is called a marginal frequency distribution, right? Because it's in the margins. Right, the bottom margin and the side margin. And this is just found by totaling things up. Okay, so this is the total frequency that we have for this whole row here and here and here, and then the pink represents the frequencies for each column. So how many total people have accomplished some college, 54,000 and change. And then this number right here is the total amount of people if you add up everyone across here, which would be our entire sample. And then if you added everyone up here, that would also be the sample size, right? Those 2 things should be the same. So again, this is our marginal frequency distribution, is just these numbers here to figure out our totals for each column and each row. Then we could go one step further, which we're going to be doing today a little bit also, and we're going to be looking at relative frequency. And if you remember, relative frequency is always piece over whole, right? It's the decimal or percentage value that you would get. So the relative frequency for a marginal distribution is you take your total, okay, that 128,000, and you put it over your entire population or your entire sample size. So they do that, you get 0.617, and then you do that with all of them. And again, if you only have 3 options for each of those people, then when you add up the probabilities of getting each of those 3 options, you should be at a total of 1, right, for 100%. So this, again, is a relative frequency marginal distribution, and it's one of the ways that we can compare stuff that is categorical data, right? The level of education, that's a category, that's qualitative, and then employment status, again, qualitative, to kind of try to determine if there's a relationship. And this was one of the things we did do in the past. Then we'd take and actually do some work with the cells, which we're going to be doing today also. And then in the past, we made a bar graph with this information to see if there was some sort of relationship between the 2. This section does cover bar graphs, 12.2. However, it's not something that's imperative that you are able to do for the assessment. So just to kind of be kind to you folks, I decided we're not going to worry about it today. So we're really going to focus on running the important tests that we need to. So first, how do we determine our expected counts? And that should sound familiar, the words expected counts, because we did that when we were doing our categorical testing in 12.1, right? There's a long way to do it and a short way to do it. I'm going to explain to you the long way, do a little bit of work for that, but then obviously we would only use the short because that's what makes sense, right? We want to be fluent and we want to be able to do things the most work in the least amount of time. Next, we're going to make sure and go over how to test for independence and dependence. Then we're going to look at another test that's very similar, but it's testing for the homogeneity of proportions, which means that all of the proportions are the same, okay? And we'll talk about that. And then because these 2 tests are so similar, when would we choose to do each of those, right? What is going to be the deciding factor that lets us know, oh, we're going to test for independence, or we're going to be doing the proportions, okay? Your homework tonight is 7 and 15. You can assume you have 1 of each of those. Okay, not a huge amount of work, but definitely make sure you get some extra practice in there. So now that we've reviewed a little bit about contingency tables, let's jump right into section 12.2. So we're going to start off with testing for independence. So we're going to be using a contingency table for this. Okay, so we're going to be looking at 2 variables. And we're going to be looking at our people that are married, so their marital status, people that are married versus single. What's their level of happiness? Okay, is their happiness have a relationship with their marital status, yes or no? And in the past, we would maybe do those marginal distributions, right? We'd kind of total up stuff here, total up stuff there, maybe figure out some information about our specific cells for our conditional relationships, and then make a graph. And maybe, honestly, you don't even remember to do those things and you just look at the total numbers. Well, you can actually test to see if these two things have a relationship between them, okay? You'd be actually figuring out if they're independent of each other, so if happiness is independent of marital status, or if they have a dependent relationship, which means that they are correlated, they do have a relationship. That's what we're testing here. We're not saying more happiness, more marital status. We're testing for, is there a relationship between these two? Are they dependent or are they independent variables? Okay. Again, looking at two specific variables, marital status and happiness. Now, to be able to start testing for independence, we are going to have to know and be able to do a handful of things. The first thing that you're going to do, just like we had to do in section 12.1, is determine your null and your alternative, okay? So, one thing that's a little different for our test of independence, and they're telling you right here, boom, look at that chi-squared again. So we're going to be dealing with our chi-squared notation and calculations, actually. So this test, sorry about that, is used to determine whether there's an association, okay? So whether there's dependent or independent relationship, an association between a row variable and a column variable in a contingency table constructed from sample data. So just like the one we just saw, your null, and this is important, okay? Your null hypothesis is always that the variables are independent or that they have no association. That is always your null. Okay, there's no equals 0. It's not that they're the same. It is that they are independent of each other. Your alternative is each and every time always that the variables are associated, which means that they do have a relationship. It means that they are dependent on one another. Okay, there's a dependent relationship between those two variables. All you need to do is just memorize these two things because that is always the case when you do a test for independence. Just like in our previous section, we're going to have to calculate expected counts. Now, expected counts are a little bit more complicated when we're dealing with a contingency table, okay? And to actually go through and calculate your expected counts by hand, it's pretty involved. So I did give you guys this example on your note sheet if you did download those examples so that you could kind of take notes on this so that you can see where it comes from. But we do have a way that we're going to do it shorthand. But I want you to understand the amount of work that would go into this originally and why the math works the way that it does. So our first step to figure out our expected counts, again, this is a pretty involved process, is to find our marginal frequencies. And then from our marginal frequencies, we're going to do our relative marginal frequencies. So we'd start by adding all four of these up. So 600 plus 63 plus 112 plus 144. And that's going to give us 919. In fact, I've already totaled these up for you folks. The next one is going to be 1,676. Below that is going to be 390. Ooh, 90. If we look at our columns being totaled up, this column is going to be 1,413. 256 here, followed by 286 here. 586 here. And then lastly, this column is going to be 730. Now, this is just a frequency marginal distribution. We would put our total amount if we summed up all these. We're going to get the exact same total if we summed up all these because it represents all of the people. And that's going to be 2,985. And we're going to use this number a lot. So we'll just circle it. So my next step is going to be to take each of these frequencies and make them relative frequencies, so piece over whole. So I'm going to take that 919 and divide it by 2,985 and get that decimal. And in this case, it's 0.308, and that's rounded. Okay. Our next one, if we divide it by 2,985 again, is going to be 0.561. And then our last one, if we were to divide it out, is going to be 0.131. Now, if we were to total up all of these, we would equal a probability of 1, because each of these decimals represents what is the percent chance, okay, what is the probability almost of someone being very happy. So 31% of people were very happy. 56-ish% of people were pretty happy, and 13% of people were not too happy. Okay, and this is assigned from our marital status. Then we'll go through and we'll actually calculate those for each of these also. So up to now, everything should feel familiar, right? We've done marginal frequencies, we've done marginal relative frequencies, whether you remember it or not. Now, to actually get the expected count, we're going to have to do some work with both of those numbers. So to get the expected count, we're going to, excuse me, we're going to find the probability of being married and very happy. Because remember, these are like probabilities, right? So in order to have the probability of being married and happy, we would have to find the probability of being married, the probability of being happy, and then maybe you remember, hopefully you remember, that the word and means that we multiply them, okay? This is the multiplication rule of probability, that if you would use the word and when describing them, meaning that they would overlap, okay, then you would just take the probability of one, the probability of the other, and multiply them together. Well, that means if we're trying to find that expected count, we would take the probability of being married, which is 0.473, and the probability of being happy, in fact, very happy, and we would multiply those two things together. So we're going to take our 0.308 and our 0.473, we'll times them together, and that'll give us our expected value. And it's like a hot mess decimal. It's 0.14, okay? 1.145684. It's a big number. All right. Now this is still just a probability. We don't actually want the probability of those two things. We want to figure out of this many people, and this is why it's getting complicated, right? So we just found the probability of being married and very happy. But now, because it's an expected value, we want to take that probability, just like we did in our old expected values, and times it by our sample size, 2,985. Okay, so when we multiply those two out, we end up getting the number around 434.8. So we'll round that up to 435 people. 400, ooh, that's hard to read, 35. Okay, so that's a long process. So let's just revisit that one more time. You find your marginal relative frequencies. Then, in order to get for the specific cell right here, we need to know the probability of being married, the probability of being very happy. We times them together to get the probability of being married and happy. And then to figure out how many people we expect would be that way, we times that by our sample size to get the 435. So let's do 720 to the side here. Okay, so in order for you to be figuring out the expected value of this, you would have to be married, which is 0.473. And we're going to times it by the probability of being pretty happy. That would include both of those, so 0.561. And then, just to save time, we would times that, right, by the sample size. 2,985. So this will give us the probability of being both. And then this, because we're timesing it by how many people there should be, tells us the percent of people that actually we can expect it to be. And that one's going to be around 793.3. And that's our expected value for here. So you can see, in this one, it was significantly higher than that 435. Here, that was 720. It's actually lower than what we would expect to see. We would expect that out of this many people, based on this probability and this probability, it should be 793 people, and that number's just a little low. So this isn't a hard calculation, right? But it's pretty labor intensive. You actually can find each of these expected frequencies a little bit easier by doing this nifty calculation here. So you still have to calculate for each of them, but instead of going through and having to find this decimal and this decimal, multiply them times the whole, it doesn't seem like a lot of work right now, but setting up all that work can take some time to figure out my expected value for just this 93 right here. I would just take my total, so I'm not looking at relative frequency, just straight up frequency. So I'm going to take my total for this row, which is 1,413. I'm going to times it by, oh, that was the column total, sorry. The row here for not too happy is 390. I'm going to times it by the column total, so I'm going to multiply those two together and then divide it by the table total, which is 2,985. Okay. And let me pull up my, actually, I think the calculator's open here. Slide that over. So 1413 times, 1413 times 390 equals, divide that by 2,985, and we get 184.6. And that's what we'll use. We'll just go out 2 decimal places. And I should have remembered what that number was. 184.6. So the larger your table, the more time consuming it's going to be to get all of these. I would have to just crunch these numbers over and over again. So I take my column total, not the relative frequency, but the total. I take this total, and it ends up being pretty much the exact same thing as if I did all of this other work, okay? And that's kind of the shortcut that people take when doing these calculations to figure out your expected frequencies that you would assume you would get in each of those columns, okay? The data that they're giving you here, this is actual observed data. The number that you're calculating here is what this potentially should have been based on the overall percent of the column and of the row, okay, and the sample size. So this is one part of the calculations we need. If you think back to what we did last lesson, we had expected outcomes, we had observed outcomes, right, or observed frequencies, and it's going to work exactly the same, okay? In fact, our test statistic for our test of independence is literally chi-squared. It's the exact same calculation, okay, that we would do for each member in each of the cells, okay? So, it's a bit of work, but what's fortunate is that our calculator is going to do this for us. But it's important that you see it is the same calculation, okay? When we're doing this categorical data, we're dealing with chi-squared. Now, something important for you to note, especially if you're going to be doing the classical method, is that to find your degrees of freedom, you're going to take your R, which stands for row, you're going to subtract 1, and then you're going to times it by the amount of columns you have and subtract that by 1, and that's going to give you your degrees of freedom, okay? So that's how you're going to get your degrees of freedom to find your critical value, okay? Otherwise, I mean, you're not going to be using necessarily degrees of freedom if you're doing the p-value test. A second thing that's important to note from this information that they're giving us here is that they give us 2 things that have to happen in order for you to run your test for independence. And they're the exact same 2 things that we saw yesterday with our categorical data. So it's running this same pattern, right? All of your frequencies have to be greater than or equal to 1. So after you found your expected ones, so after you crunch these numbers, right? The 435, the 793, the 184.6, and you'll do it the shorthand way, right? After you've calculated these, you need to make sure that they're all equal or greater than 1. You also have to make sure that no more than 20% of those expected values are going to be less than 5, right? We can't have more than 20% being smaller than 5, and all of them must be greater than or equal to 1. Okay? So that's always something that we're going to have to check. We don't check for normality. We don't check for any of those other things. This is what we're looking for. So I did do this slide again just to show you the similarities between the two. I want to drive home the fact that the null and the alternative are going to be pretty much the same every time, just with a little bit different verbiage, okay? So you'll say whatever the row variable is, whatever the column variable is, and the null is that they are independent. It is this case every single time. Your alternative is going to be that the row variable and the column variable are dependent on each other. Okay, that's why we're testing for independence, because we're testing the null. That's what we assume to be true until we have enough evidence to say, nope, we have enough evidence to say they do depend on each other. You folks aren't going to be choosing a level of significance. They'll be given to you. And then you need to calculate your expected frequencies before you do anything else, okay, for each cell in that contingency table. After you've done that, you can then verify those two pieces and parts, right? You can't actually figure out if they're greater than or equal to 1 until you've calculated all of your expected frequencies. You can't figure out if there's more than 20% or less than 20% of them are less than 5, okay, until you actually calculate your expected frequencies. Once you've gone through, you develop your hypotheses, you identify your level of significance, you calculate your expected frequencies, you check these two. At this point, you'll hop on your calculator, run some tests to get the test statistic, and then you'll go either to classical or you'll go over to your p-value, okay? That'll be at this point. Or both. Some of you have still been taking advantage of that, and that's still going to be something that's available to you in our Chapter 12 exam. So we're going to actually do a chi-square test for independence on this same table that we've seen over and over and over again so far in this section. And so we already have a couple of these here that we'll use. Let's see. This one is 435.025. Okay. In fact, folks, I'm going to write these all in, and then I have another surprise for you later once we're running our test, okay? But for now, I'm just going to stop talking, speed up the video, and write them all in for you. All right, folks. So I've written all of our expected frequencies in here. I went out of order. I was just so hip to getting those written in. We should have started out with our null and our alternative. Okay. So our null is that these two items are independent of each other, and that's what I'm going to write. But I'm not going to put that they're independent. I'm going to put the actual labels. So I'm going to start out with my row label, and then I list my column label second. So I'm going to say happiness. And marital status are independent of each other. All right. This is really frustrating with this pen. I'm sorry. That means my alternative is going to be that they are dependent, which means they are related. Remember, independent means that these two variables have no relationship, okay? So it doesn't matter what your marital status is, it has no relationship with your happiness, okay? The alternative is that there is a relationship between them, that they are dependent, okay? So happiness and marital status are dependent, which means they have a relationship. Okay, so we do this first. After we've done that, we should make sure we understand what our alpha is. Our alpha, they told us, is 0.05. And then we're going to head over, figure out all our expected values, which I already did. And now that we have the expected values, we can check for our two things. Okay. The first thing we're looking for are all of our frequencies greater than 1, or they could be equal to 1. That's fine. Okay. So we're going to look over here. Obviously, all of these are bigger than or equal to 1. So that's good to go. The second thing that we need to test for is going to be, is there less than 20% of our data that is 5 or smaller? So if I look, there's no data that is 5 or smaller anyways, so clearly it's not going to be more than 20% because it's 0%. So both of those things work. Now that I've done all of this pre-work, which that's a lot, okay, I'm ready to start doing my test for independence to be able to answer my null and my alternative. So to be able to do this, we're actually going to go into a new menu on our calculators, and I'm going to write down the keystrokes here, and then we'll go into the calculator and actually do it. So in order to put in all of this information, we can't just put it as into like an XY chart, right? We can't put it into L1, L2. It's an actual table. So we can model tables with matrices, and some of you maybe learned about matrices in Algebra 2 or in pre-calculus. We no longer cover it in Algebra 2, so you maybe haven't seen it depending on when you took Algebra 2. So anyways, to get to that menu on your calculator, you're going to press the second button, and then there's an inverse X button like this, and if you look above it, that's actually where the matrix is found, okay? So to open the matrix menu, you're going to press those two buttons. Once you're in there, you're going to go over to edit, and it's not the first option. You actually have to go over, press over twice to get to it. Once you've gone into edit, you have to say the dimensions, and they always do how many rows and how many columns. So you're going to make sure to type in row amount by column amount. After you've done that, you're just going to fill in your entire table, and what you're entering is your observed data. Okay. So we'll go through those keystrokes right now so you can see them. So we'll clear this out. You can see right here it says matrix. See how it's over the inverse X button? So I'm going to go second, matrix. And you can see right here, boom, it's not names. Names is how you pull up the labels. We want to go over to edit. So you press over twice, and we're going to edit A. We're going to make this has 3 rows, so it is going to be 3. And then our amount of columns is going to be 4. And you can see that as you do it, folks, it's creating it for you. Now, it might not look exactly like this on your screen, but it's showing you zeros as placeholders. Then you are literally going to type in this table into the matrix, okay? Right where each cell belongs. So I'll take a second and type those in. Remember, you are doing the observed values, which is like the 600, the 720, the 93. You are not putting expected into matrix A. All right. So now that I have my whole table in matrix A, I'm ready to actually start running my test. So we'll write down the steps here, and then we'll come back to the calculator right afterwards. So the next steps that we're going to take to actually run the test is we're going to go, like we always go, into stat. We're going to go into our test menu. And then you want to ask yourself, what's our test statistic here? It's chi-squared. So we're going to go down to chi-squared, and we're actually going to go right down to chi-squared test, which is right above the goodness of fit test that we did in our previous lesson. And from there, we're going to be able to get our test statistics. We're going to be able to get our p-value. So stat, over to tests, down to chi-squared test right here. It's option C on my calculator. I'm going to press enter. Now, your observed has to be an A, okay? Your expected is going to have to be in B. You ready for some really good news? That was like an intentional pause. It would have been like a pause with me giving you an eyebrow in class, and you would have been like, what is she getting at? What I'm getting at is that your calculator does not need you to fill in the expected. When you run the chi-squared test, it is going to take your observed, it is going to do all of that work for your expected and put it in B for you. And then you're going to just be able to calculate. Now, I know you're like, oh, Miss White, you just copied down all of those into this table. You made me feel like I had to do it. Well, remember, before you run this test, you technically need to make sure that those two assumptions are true, okay, right? That all of your frequencies are greater than or equal to 1, and that you don't have too many that are 5 or below, okay? And so I didn't want to bring this up then, but we're not going to ever do those calculations for expecteds. We're just going to check it out here, and I'll show you how to do it after we do the test. And we're going to get those values and just double check those two things that we need to kind of after running the test. So here we get our test statistic, which is 224.114 0.56. And then we have our p-value, which is 1.3 hot mess. And then it has E negative 45, which means I would move this decimal point forward 45 spaces. It is pretty much 0, right? It's going to have 44 zeros after the decimal point before you get to the 1. Now, it does tell us that our degrees of freedom are 6. We do need to know that for our classical method. Okay, so I'm just going to transfer this down to our slide and we'll keep going. Excuse me. All right, so our test statistic is chi-squared here. And our value for that again was 224.1136. And our p-value is 1.3 mess e to the negative 45. So we're going to say that's approximately 0. Okay, it's going to have 44 zeros in front of that 1. So is 0 less than 0.05? Heck yes, it is. Okay, so right now we're saying there is enough evidence to reject our null and accept our alternative. So we would say something like, there is enough evidence at a 0.05 level of significance to say happiness and marital status are dependent variables. Okay, or you could say that there is a relationship between happiness and marital status. Not anything about the relationship. That would have to be a correlation test. Okay, and we're actually not going to get to that chapter. That's chapter 14. We're done after this chapter. So just that they have a relationship, make sure you're very careful with your wording. If you wanted to do classical method, you're going to draw your chi-squared graph in. It's always going to be the shaded to the right. We're going to have to calculate our chi-squared for 0.05. And this time, if you look back a couple slides, our degrees of freedom, it did say on our calculator how to do it, but I want to remind you, it's 1 less your rows, 1 less your columns multiplied together. I told you it'd come in handy knowing that. Oops. So our degrees of freedom, if there's 3 rows, I'm going to do 2. If there's 4 columns, there's 3. 2 times 3 is 6. So I'm going to use degrees of freedom being 6. I'm going to go to table 8 in the back of my book. And table 8 in the back of my book for 6 degrees of freedom is going to tell me that this chi-square value is 12.592. So I ask myself, is my test statistic in the critical area? Yes, it's in that shaded region. So yes, there is enough evidence. Heck yes, there's a lot of evidence actually. See how strong that is and how strong that is? It definitely is, there definitely is a relationship between those 2 variables. Okay? And that's what we're testing. There's a dependent relationship between those 2 variables. So this is one of the 2 tests, and it focuses on when you have 2 separate variables. In the same section is the test for homogeneity of proportions. And again, this is a chi-squared test, so we're still using that as our test statistic. But here, it's a little different. It's going to feel similar, but it's not. This is testing whether different populations have the same proportion of individuals with the same characteristic, okay? So if you think to this problem, you have one population, and it's like the whatever 1,000 people that were surveyed here, 2,000 and something, right? One population, 2 separate variables. Is there a relationship between the variables? When we're doing this one, we have several populations, and each population is going to have some sort of characteristic that we're measuring, and we want to see, are the proportions of individuals in each of those populations equivalent to each other? So are they the same? Are all the proportions of people, regardless of the different populations, the exact same? Okay, that have that whatever that characteristic is, and it will make sense as we do our example here. So like I said, it is a chi-squared test. It's going to look super duper similar to the ones we just did, right? This looks like a contingency table. It is not. This is just a 2-way table, okay? There isn't 2 separate variables measured here. There is 1 variable. This is our variable. These are our 3 separate populations, our 3 separate groups, right? So we're comparing across different populations on the same specific characteristics, okay? 3 separate populations. That lets me know that I am doing this specific test. So let's read this problem and then we'll go through the hypothesis test. Good news, the hypothesis test for this is identical, okay, identical to what we do for our other test in this section, okay? It's the exact same thing as the test for independence. So anyways, Zocor is a drug manufactured by Merck & Co. that is meant to reduce the level of LDL cholesterol and increase the level of HDL cholesterol. In clinical trials of the drug, patients were randomly divided into 3 groups. Group 1 received Zocor, Group 2 received a placebo, and Group 3 received, I can't even say that, which is a different cholesterol-lowering drug that is currently available. Table 12 contains the number of patients in each group who did and did not experience abdominal pain as a side effect. So they either had abdominal pain, which is this, or they did not have abdominal pain, which was this. Is there evidence to indicate that the proportion of subjects in each group who experienced abdominal pain is different at a 0.01 level of significance? Okay, so that's pretty strict, a 1% level of significance. So you notice it's a two-way table. You notice that it's different populations. So you say to yourself, I'm checking to see if these population proportions are the same. Homogeneity of proportions. That's what I'm going to do. Okay. Just like with our other problems, their null and alternative should be written first. And our null for always these types are going to be that each of our proportions are going to be identical. So if we take our first proportion from our first population, it should equal the second. And because we have 3 here, it should equal the third. This is how we're going to always model our null hypotheses when we're doing these. Our alternative hypothesis is going to be that at least one of these is different. So this feels similar to section 12.1 too, right? At least one is different. If at least one is different, then that means they're not all the same, and that's what we're testing for. Our alpha is going to be, again, 1%, so that's that step. Our next step would be to examine our expected values and then figure out our number 1 and our number 2, okay? Our frequencies, are there any that are less than 1? If there is, that's not a good sign. And then are there any values that are less than 5? You can only have 20% of those. So normally we'd total this up, times those 2 totals, and divide by the total amount of people surveyed. But I told you in our last example, and I said I would go back to it with that one, and I didn't, that you can actually have your calculator do this whole expected values for you. So we're going to skip this and come back to it momentarily, and we're going to go back down to our test. So instead of writing all the keystrokes for our test, we'll just hop right onto our calculator. We're going to enter our table into the calculator, and we do that by creating a matrix. So we're going to go second matrix. We go over to edit, right? Because we want to edit it, and we're going to go to A. And I'm going to delete out 3. And my current table had 2 rows, so I'm going to put 2. And it had 3 different populations, right, as columns, so I'm going to put 3. Now it did keep in my previous values. I can just delete them as I go and replace them. So I don't have it up on my screen right now, but I do have a worksheet here. In that first cell, it's going to be 51, followed by 5, followed by 16. And then the next ones are 1,532, followed by 152, and 163. Nice smaller table, okay? So we have all of our cells in. There's our little two-way table. I am ready to run my statistical test. So I go stats. I'm going to go over to tests. My test statistic is chi-squared. So I'm going to go down to chi-squared test. It is not a goodness of fit. I go right here and I press enter. Now, remember how last time we just like checked this out and checked that out and calculated it? We're going to do that too. Okay, and I'm going to come back to the screen in a moment. And there we go. We get our p-value. We get our chi-squared value. You should write those down on your paper. I have them written down. No big deal. But what I want to show you is that once you run this test, okay, you've input all of the data from this test, including the expected values, into matrix B. So if we come back to our matrix menu, so second inverse of x to pull up matrix, we're going to go over to edit and down to matrix B and just press enter. these are all of your expected values. How freaking awesome is that, right? You don't have to calculate all of those by hand. They are here on your calculator. So now, after we write down our other data, we can just go back and double check that the two assumptions that we need to assume, that we need to make about our data is true. Okay, so are there any cells that are less than 1? No. Is there 20% of or less that are less than 5? So none of them are less than 5. This is close, but no, so I don't have to worry about it. Sweet. My hypothesis test, which it isn't a hypothesis test, my homogeneity of proportions test is going to be valid. Okay, so I'm going to go back now. So I'm going to go back here. I just checked out my expected values. I didn't write them down, but I did check them, and I know that my F value is going to be less than 1. I know that I do not have to worry about 20% being less than 5 because none of them were less than 5. And I did get some information. I got my test statistic, chi-squared. And if you did not write it down, the chi-squared value for that was 14.7065. And my p-value, again, it was written in scientific notation. It was 6.4 and change with an e to the negative 4. And what this means is I would move that decimal point forwards 4 places, 1, 2, 3, 4. So I'd have 3 zeros in front of it. So I technically have 1, 2, 3 zeros, a 6, less than, again, it's 1%, because it's pretty severe. We don't want people to have side effects, okay? And look, that and that, right? This and this, that's true, right? Yes. I would reject my null and accept my alternative. So I would say something like, there's enough evidence at a 0.01 level of significance to say that at least one of these medicines reacted differently than the others, okay? Or one of these groups was different than the others, okay? So that's what I'm looking at, is I'm comparing across the groups, and I need to be able to say that both in my null and my alternative hypotheses, but I need to be able to also say that when I do my conclusion piece for this, right? I need to say that at least one of the population proportions is different. So let's say you were doing the classical. It's the exact same as before. I'm looking at chi-squared for 1% right now. There are 2 of these and 3 of these, so I have 1 times 2, which is 2. I'm going to do degrees of freedom equaling 2. And then I'm going to go to the back of my book, go to this graph, and it's going to tell me that my critical value is 9.210. And clearly 14 is going to be in the shaded region, right? If this cutoff value is 9.2. So it's giving me the exact same conclusion that the p-value tested, that yes, we do have enough evidence at a 0.01 level of significance to say that out of the 3 proportions, at least one of them is different. So the math for both of these is the same, right? But setting up your null and your alternative is very different, and writing your conclusion is actually also different. So it's important that you understand, when do I do each test? And if you think back to chapter 11, and I'm letting you know it's going to be on chapter 12, you're going to have a question under each question that says, which test are you going to do here? And you need to be able to tell me you're either doing the homogeneity of proportions or that you're going to be doing a test for independence. Okay, so here are the things that I look at to delineate which one's which. Both of them are going to look like a two-way table, okay? If you are measuring 2 separate variables, that means it's a contingency table, and you're only looking at one total group, okay? One group is being asked 2 questions about one for each of those variables, and you're trying to determine dependence, okay? They also might say in the problem that, is there a relationship? Okay, those 2 are going to be keywords that you are specifically, even though the keystrokes are the same for both of them, that you are doing a test for independence. Okay, that's what you're going to look for. If there are 2 or more populations and they're going to be represented as columns, so look at your columns. Is that a variable or is it representing different groups? If it's 2 or more different groups, then that's going to tell you automatically that you're doing the homogeneity of proportions. Okay, you're going to know that right off the bat. If it's one variable being measured and it's only on the left-hand side, and if they're asking you in the problem something about the equity of the proportions, and it doesn't have to say equity, it could say something like, are the proportions the same? Is there a difference? Now be careful, because we see difference in a lot of tests, right? So make sure you notice that it's a two-way table, that it's looking at several populations, 2 or more, and that you're only measuring one variable. Okay, and that's going to be your key for that, is that you're looking for same or difference there. And this again is going to be our homogeneity test for homogeneity of proportions. Again, you only have 2 homework problems. One will be one will be of the other. But know that on that Chapter 12 exam, there's only 6 problems, okay? You're probably going to have one of these and one of these, and then 2 from each of the other sections, okay? Hang on tight, folks. There's only one lesson left of totally new learning, and then it's review, taking a test, and then that little mini project, and we're done, okay? Thank you, folks. If you have any questions, please consider attending office hours. I will see you and talk to you later. Bye.